In this video, we work through an example problem that is similar to one of your homework problems. It's actually a very simple, I think elegant idea that relies on the fact that finding center of mass or centroids is additive. So let's say this is our region. And I haven't done a very good job with my picture, but this is a rectangle, and that's a rectangle, and that's a rectangle. So I've got a simple plane region it's basically the union of these three rectangles. They're all taking up, or they're all in the same xy plane. Well, it turns out if I want to find the center of mass of this thing, all I have to do is find the center of mass of each of these guys, find the mass of each of those three rectangles, and then find the appropriate moments and mass of the whole thing. Now, if we assume that density is equal to a constant, and that's usually what they're asking you to do. We'll say density rho is equal to a constant. The densities are going to cancel out anyway, so we don't really need that constant. We can just assume that density is equal to 1. In that case, the mass is going to be equal to density, that's mass per unit area, times area. And since mass per unit area is 1, mass and area are going to be the same thing for each of these rectangles. So I'm going to split this into 3 rectangles that are easy to find the center of mass of. That's my first one, that's my second one, and that's my third. So I'm going to think of these as 3 separate pieces. The mass or area of the first one is just length times width. If my origin is right here, this is x equals 1, this is y equals 3. So my mass is the same as the area, so it's just 3 times 1, or 3. For the second one, mass is the same as the area, that's 1 times 2. So I'm going to write area of 3 here. Here I've got an area of 2. And this is also an area of 2. And area and mass are the same thing if we assume constant density, or a density of 1. Okay, and then because of symmetry, these are rectangles. We know exactly where the center of mass is. It's going to have to be given by the average x value here and the average y value. Well, the average x value between 0 and 1 for mass 1 is the average of 0 and 1, so it's going to be 1 plus 0 divided by 2, which is 1/2, which makes sense. It's exactly halfway in between 0 and 1. And the distance for the y's is 3, so halfway in between. 3 plus 0 divided by 2, the average y value is 3 over 2. Or if you prefer, it's just 0.5 and 1.5. So I guess I shouldn't have drawn that right on here. But that's my center of mass. It's at 0.5 and 1.5. Now here, the center of mass is going to be halfway between 1 and 3. That's the x-coordinate anyway. Halfway between 1 and 3 is 2, or you could just take the average x value. 1 plus 3 divided by 2 is going to give you 2. Does that make sense? And the average y value, well, y is going from 0 to 1, so we're going to add 1 and 0 and divide by 2, and you get 1/2. So the center of mass for this piece is 2 and 1/2. And the center of mass for this last one, this is always assuming constant density. Center of mass and centroids are the same thing. X is between 3 and 4. So we're going to add 3 and 4 and divide by 2. So we get 7 over 2, or if you prefer, 3.5. And then for the average y value, y is going from 0 to 2, so we're going to have 2 plus 0 divided by 2. The average y value is going to be 1, which I think makes sense. So we're right here. Now, instead of evaluating those integrals that we did in the last section, I can think of all of the mass on this area being concentrated at its center of mass, and all of the mass on this area being concentrated at its center of mass, and all the mass on this area being concentrated at its center of mass. And so this problem, which looks like the mass of a planar lamina problem with lots of different curves, it looks kind of complicated, is actually extraordinarily easy. I'm just going to find the center of mass of the system that would consist of 3 point masses located at this location, and this location with these masses. So it's just like one of our center of mass problems from in 2D that we talked about earlier. So let's look at the moment of the system or let's do total mass first. It's going to be the sum of the 3 masses. So we get 3 plus 2 plus 2, so we get 7. And then the moment about the x-axis. Comes from taking the distance, or the mass of each of those, and multiplying by the distance to the x-axis in each case. The distance to the x-axis in each case is going to be the y values. For I equals 1 through 3, because we only have 3 rectangles. So I have the mass of the first one, which is 3, times that y value, which is 1.5. Or if you prefer, you could do 3 times 1.5. Plus this mass, 2, times the y value there, which is 1/2. Plus this mass, which was also 2, times the y value there, which is 1. And so I get 4.5 plus 1 plus 2. So that's 3 plus 4.5 is 7.5. And that's the moment about the x-axis. To find the moment about the y-axis, we do the same thing. We're taking each of the masses and we're multiplying by the distance to the y-axis. But the distance of each center of mass to the y-axis is just the x value. I'm going to do those in a different color. So there's that right there, and that right there. Oops, not that. That right there, and then that right there. It's pretty far. Okay, so for the first one, the distance to the y-axis is the x value. We have our first mass, which is 3, and the distance to the y-axis is 1/2. Or you could just take that 3 and multiply by the 1/2. And then the moment for this particular piece is that mass, which is 2, same as the area, times the distance to the y-axis, which is 2 units, because that's x equals 2. Or you could just do 2 times 2, which is the same thing. And then on this last one, I've got the mass of this guy, which is the same as the area of that guy, times the distance to the y-axis, and it looks like that's 3, that's 4. The distance to the y-axis is 3.5. Or you could just take that 2 and multiply it by the x value there. When you add these together, you get 1.5 plus 4, plus what's that? 6 plus another 1 is 7. So we've got 11 plus 1.5 is 12.5. That's the moment about the y-axis of the entire system. Isn't that nice? We just took this thing that was planar and we simplified it by thinking of concentrating all of the mass at a single point. And it turns out that that's completely legal. That's the balance point for that entire rectangle. Okay, so I found the mass, I found the moments about each axis, and now I can use those to find the center of mass. I'm going to take the moment about the y-axis and divide by the total mass to get x bar, and take the moment about the x-axis and divide by the total mass to get y bar. Moment about the y-axis is 12.5, and we're dividing by the total mass of 7. Moment about the x-axis is 7.5, and we're dividing by the total mass of 7. And let me get my calculator out to do the simple arithmetic. So I end up with 25 over 14. And you can guess the next answer, 15 over 14. And say, well, what does that really mean? Well, this one's 1.07 approximately. And 25 over 14 is about 1.79 approximately. So the center of mass of this entire system lies at the point x equals 1.79, so here, y equals 1.7. You're like, ooh, that's not even in our region. That happens though, because you've got some mass over here on this side. It's because of this U shape that we have a center of mass that's not in the region. Okay, so that is a simple example. You've got a problem that's similar on your homework. If you see a rectangle like this, and this is between x equals a and x equals b and y equals c and y equals d, the center of mass lies exactly where you think it would. You just take the average x value and the average y value. For a rectangle, that works. Now for a circle, if it's completely symmetric, the circle, the center of mass is, you guessed it, the center of the circle. Center is at the location AB. So keep these two in mind as you do the homework. And in the next video, we'll talk about finding the center of mass of a triangle, which is very important. It comes up a lot in engineering.